Page 5. Page 5 first has the discussion on how the particles of a solid compare to those found in a gas. If I was to draw them, which we did earlier, the solids are going to be arranged nice and neatly. They are touching and vibrating, whereas the gases are moving, bouncing around the container. So compare how the particles of a solid compare the particles in a solid are neatly arranged and touching. Gas particles moving and bouncing off each other. And if they're in a container, they're bouncing off the walls of a container. Next one, define following vocab words. The atomic mass one, it's more of a chemistry thing, has to do with how much a mole of a substance weighs, so we're just going to cross that off. Atomic number, on the other hand, that's the number of protons in an element. A lot of people will look on their periodic table, and they'll also say it's the number of electrons as well, but it not always is. If it forms an ion, it's not the number of electrons. So the definition would be protons. Mass number. According to our periodic table, the mass number is the protons plus the neutrons. It's just a number got by adding the protons. Protons plus neutrons. And when we draw isotopes, they are different versions of the same atom or the same element. They have the same number of protons, they have different number of neutrons. Down to atomic structure then, putting that into practice. It's going to say draw a Bohr's atomic model. A Bohr's atomic model would have a nucleus with a certain amount of protons and a certain amount of neutrons. And then it should have shells that go outside or levels. Well, that makes a big old mess. So what we usually do is just simply cut it off to just one side and wherever we need them, and that's all we need to have. Our mission then is to figure out how many protons, how many neutrons, and how many electrons, and where are they. Atomic number is 9. That means 9 protons. But its mass is 19. That's the total number of protons plus neutrons. So 19 minus 9, that 9, equals 10. It's going to have 10 neutrons. Now, if it does have 9 protons, it also has 9 electrons. Where are they? 2 of them in the first energy level, because that's all it can hold. The other 7 can fit into this energy level, so I don't even need this. If it asked how, it doesn't ask about that. If I'm going to draw 3 different isotopes of something like sulfur, and it's going to tell me one of them is sulfur 31, the other one is sulfur 32, and sulfur 33. So I'm going to draw Bohr's model for each of these. Every one of them is sulfur. According to the periodic table, sulfur has 16 protons. So every one of these is going to have 16 protons, 16 protons, 16 protons. Therefore, every one of them has 16 electrons. Where do I put them? 2 can fit in the first, that's full. 8 can fit in the second, that's now full. I only need 6 more and they can fit in the third. All those would be there. And I can do the same thing here. So these are very similar. Isotopes are different versions of the same electron. The only difference is their number of neutrons. So here's the only difference. Let me go to the first one. Sulfur's 31. I can see that 16 of that is protons. 31 minus 16, there must be 15 neutrons. This one is 32. One more than that If it only difference is in number of neutrons, it must have one more neutron, 16 neutrons. And finally, 33 minus 16 equals 17 neutrons there. Next page. What are we going to say about differences between ionic and molecular or covalent? Well, I remember they wrote it down here that says something about molecular are nonmetal to nonmetal. So when I go to this one here, differences between them. Molecular are non-metal to non-metal. There's one difference. And what else could I say? The other, like ionics, are metal to non-metal. Metal to non-metal. And when we drew these, or when we make formulas, we know that positive charges stick to negatives if we're dealing with an ionic bond. But in a molecular or covalent, that was like when we had Cl with 1, 2, 3, 4, 5, 6, 7 electrons. This is a Lewis dot. And another Cl with 1, 2, 3, 4, 5, 6, 7 electrons. It looks as though this has 8 electrons. And it looks as though this has 8 electrons because they share electrons. Huh. So it's dawning on me that this and this and this probably could have just been my example. Example, Cl2 is a molecular or covalent. I could have used carbon dioxide, CH4. There was all kinds of them we drew, but any of the diatomics work fairly well. Ionic bonds are things like sodium sticking to chlorine. Sodium has 11 protons, Na. And when we went through it, it had 2 in the first, 8 in the second, and 1 valence. Chlorine had 17 protons, and its electrons were 2 in the first, 8 in the second, 7 in the third. And we had this idea that, well, this one, in order to be happy, wants to lose 1. This one wants to gain 1. So if I erase this one, and if I made this 8, now this has a negative charge. It's chlorine with a -1 charge. And this one has now a positive charge. There's one more proton than electron. So sodium chloride is a positive sticking to a negative versus chlorine is them sharing atoms, sharing electrons.